Hi everyone, my name is Quinn Slack and I'm from Sourcegraph. I'm going to talk to you about how we built Sourcegraph in Go. Sourcegraph is a large-scale code search engine that's out there right now for you to start using. So I'll talk about what Sourcegraph is, I'll talk about why we chose Go, and then we'll dig into how we actually built Sourcegraph using Go. Sourcegraph is a large-scale code search engine written in Go, which means that not only does it go and index a ton of open source code that's out there, it also analyzes it at a semantic level, just like a compiler. So that means it can show you usage examples, and you can search for functions and packages by name. It supports Go, Python, JavaScript, Ruby, and some other languages soon. So let's take a look at it. So here on sourcegraph.com, you can type in the name of a function, and in this top screenshot you see that I found the new request function from Go. Just typed in new request and it found that for me. And then I can pull up a function. That's a screenshot you see below. And on the left, I see a code view. Everything is fully linked, just like Wikipedia. You can click and go to any definition. And on the right, I see quick documentation for what I'm looking at and examples from other open source projects that use this function or package. So it's a really good way to not only see how to use a piece of code, but also see the best way or the idiomatic way to use a piece of code. Why did we choose Go? There are two questions here. First is, why did we choose Go initially? And the second is, why do we keep using Go? First answer to why did we choose Go initially is that Go makes it super easy to do source code analysis of itself. And so when we were prototyping Sourcegraph, it was the obvious choice. And actually, it might be more accurate to say that Go chose us. When we first tried GoDoc, we loved it. We thought it would be super useful if there was a similar tool that worked for every other language, was public, was globally searchable, and supported cross-referenced examples. And that's a lot of what Sourcegraph is today. So we owe a lot to the Go team's vision of how programming tools should be. And the answer to the second question, why do we choose to use Go every day when we wake up? Well, that's more important, and I think that the rest of this talk will answer that. So let's dig into how we built Sourcegraph using Go. There are two parts to Sourcegraph. One is a large Go web app, has an HTML front end, an API, and it's a database in the back end. And this is what you see at sourcegraph.com. The second part is a standalone command line tool that analyzes code from projects. And let's start out with the Go web app. So we're going to go through how we built our large web app in Go. And here's what the architecture looks like. The app has three layers: the web front end, which returns HTML, the HTTP API, which returns JSON, and the data store at the bottom, which runs SQL queries against our database and returns the results as Go structs or slices. So the way that it all works when a request comes in is the web front end gets the request and issues a number of API calls to get the data it needs to render the page for the client. And the API will call into the data store, which will call into SQL. And finally, the results trickle back up. Finally, the web front end gets the results as JSON, parses them, and then passes them to some template, and finally renders the HTML. This multi-layer structure is pretty common for large web apps, and there's some really nice ways that Go makes it super simple to implement. Our goals in implementing this were two. We wanted to avoid complexity, and we wanted to avoid code repetition. In our experience building large web apps, complexity is really easy to creep in because you always push the limits of whatever web framework you're using when you make a large app, and you end up twisting the abstractions in a really ugly way, and that yields complexity. And whenever you make a multi-layer app, you often have a lot of repetition because you find yourselves re-implementing or remodeling the same concepts in multiple layers in varying levels of detail or at varying levels of abstraction. So how do we avoid complexity and avoid repetition using Go? These are the main points. No framework using interfaces. We have a high-quality API client. We unify our URL routes and URL generation, and we share parameter structs. Those are the 5 ones I'm going to cover, and we have a bunch more that I list and we'll go into in another talk. So first one is really important. We don't use a traditional web framework. We use NetHTTP in the standard library and the Gorilla Mux router instead of a web framework. As I said, we found that large web apps really twist the abstractions of any web framework anyway, and a lot of the value that they provide in other languages is unnecessary when you're using Go. For example, when you're handling errors in API endpoints or HTTP handlers, other frameworks will often have some way of handling the errors and propagating them up, but in Go it's super simple. We made a simple wrapper function so that we could write handlers that returned an actual error, as you can see in this code example. Serve XYZ returns error type, and our little wrapper function will check the return value and send the proper error to the HTTP response writer if there is an error. This wrapper function is about 20 to 25 lines, and it also checks authentication and records some other data. And this essentially replaces what a framework would do for us, except it's all custom and it's very simple. We also use global variables instead of per request context data for database connections and config and so on. A lot of frameworks will have some dependency injection or some other method of injection for getting each request the right set of per request handles, but this is unnecessary in Go. I'll go into this later, but in Go you can use global variables for a lot of things that other languages and frameworks would have you use much more complex methods for. And as I said, we use Gorilla Mux as a router. It's super simple and it integrates really well with NetHTTP. And then to render the response in either HTML or JSON, we have little helper functions. And again, in a framework, these would be provided for you, but they'd be a black box. We've written these on our own. They're very simple, and they essentially use the Go standard library. They just make a few calls to it. And so that's how we built this big web app with no framework. Let's go into some more details. So the way we started building our web app was we determined for every noun in our system what actions we would need to perform on it. So let's take repositories as an example. Just like GitHub, repositories are a key noun in our site. That means Git repositories, Mercurial repositories, anything that holds code. And the kinds of actions that we want to perform on this resource are get and list and search and some others that I've omitted here. But get, list, and search are the big ones. And we see these methods implemented in two places. One is in our API client, and this will go and hit our HTTP API and get the data that way. And the other is in our data store, where these method implementations will actually issue SQL and go query a database and get the results back. So these interfaces really form the core of our system. We have one for each noun, so we have about 8 in total. And these interfaces are a really good way to get up to speed on how Sourcegraph works internally. For example, we recently had an intern join, and he was able to get a really quick idea of what Sourcegraph did and what the capabilities were based on looking at these interfaces. So here's what the implementation of the data store interface method get would look like. It is simplified a little bit, but I just want to make it really concrete. So here it's repo store, and that contains some database connection, and it will just issue SQL and read the response back into a struct. In our case, we use JMoiron's model, which is based on GORP, but a lot of other SQL libraries will work in this way, where you can serialize a SQL result set into a struct. And then the API client method is really similar. It will create the URL based on our API, and you can see we've hard-coded it here. I'll go into a way that we can avoid hard-coding it later, but we'll leave this as is for now. So it constructs the URL, and then it just issues an HTTP request and parses the JSON response. So again, super simple. And what this means when we have one unified interface for all the different ways we want to access the nouns in our system is it makes it really consistent and simple to actually use these, and it makes our handlers really simple, both our front-end HTTP handlers and our API HTTP handlers that return JSON. So let's take a look at the front-end handler. You know, the ideal HTTP handler would really just concern itself with the request and HTTP stuff related to the request and the response, which is HTML or JSON in our case. And we've achieved that. So we pull in the front-end handler, we pull the name out of the route, and then we just look it up in the API client and we print HTML. In reality, we use HTML template to do this, but this is a simplified example. And there's not a lot of other stuff in this handler. There's no constructing another HTTP request, there's no database calls or anything. This HTTP handler literally handles an HTTP request and not much else, which is really nice. And same for our API handler. You can see that it calls the same method, get, on the repo store, which will hit the database directly. And then it writes some HTTP headers, the last modified header, and we also look at authorization and some other things in these headers. And then it returns the JSON. So, again, super simple. These are very much only concerned with HTTP related things, as HTTP handlers should be, and they're very easy to read. We also get some other benefits out of having a very small number of unified interfaces in our system. For one, it means that we dog food our APIs, so our front end will use the same API that our back end uses, and other people who want to build on our site will also use that same API. In fact, we have open sourced these interface definitions, such as the repository service that I showed you, and that means that we are forced to use the same API that everyone else does, and so hopefully that means that it'll be higher quality, because we don't want to inflict pain on ourselves. We love our users, but it keeps us honest. Another thing is, by using HTTP as the interface between our front end and our API, and doing that transparently with the API client, we can just use all the standard HTTP box of tricks, load balancing, caching, and authorization schemes, and we don't have to reinvent them in Go or some other layer. So previously, when we looked at the API client, we saw that we were constructing the URL by hand using func.sprintf. There's actually a better way, and the reason why we want a better way is because you have to imagine that if we're constructing the URL in the API client, we're also going to repeat that hard-coded definition somewhere in the server so that the server can recognize that path. And that's bad. We have a lot of API routes. We have about 70, and it gets really easy for them to get out of sync. And so our API client will make a request that our backend doesn't recognize. So the way to solve that is to separate the route definition from the actual attachment of handlers to the routes. And here's a simple example of how we can do this. This is using Gorilla Mux, but a lot of other routing packages also offer this functionality. So you have one function that constructs the router. Here it's new API router, and we just define the routes and give them a name. We don't attach a handler. And the returned router from this function will be used by the API client to generate the URLs, which it has all the information necessary to do, and it'll also be used by the server to actually attach the handlers. And let's see how that looks down below. In the init function, we can see we are going to get the router, and then we're going to actually mount handlers on it. So we just call m.get and then the name of the route, and then handler func. And that's just a standard Gorilla Mux feature that will just mount a handler func at that named route. And so there we have it. It's impossible for our API backend routes to diverge from what our client knows. So we've eliminated a large class of bugs that we had seen a lot. So once we have the router definition separated like this, here's how we can go back to that previous API client method and eliminate the hard-coded URL. Instead of using func.sprintf and making the string manually, we just call API-router.get, and again we get the named route, and then we call .url on it. And URL is a standard Gorilla Mux feature that will just generate the URL based on that route, essentially reverse routing. Another thing that we do to save a lot of code and avoid repetition is to share the parameter structs that we use for the interface methods. Now we're kind of forced to do this because we use the same interface method signature for our API client methods as for our data store methods. And that's really great. Because initially we had 3 different parameter sets for each interface. That would be the front-end query string parameters, what's in the URL query string to the front end in people's browsers, the API query string, and the data store method parameters. And these 3 were mostly the same, but they differed a little bit, and we didn't have the Go compiler's help in ensuring that they were the same. So by sharing parameter structs at the Go level, we have the Go compiler's help to make sure that these are always the same. So this search option struct at the top is the option struct for the search method on repositories. And it has just 2 fields, owner and language. The actual one has more. And again, we've open sourced the actual one, so you can check it out in our code. And so what this means is in our front end, in our API, you can go to /API/repositories/search $language equals Ruby or Go. And that $language equals query string parameter corresponds to this language field. And in fact, when the API handler or any other HTTP handler receives that query string, we see how it decodes it in the next snippet of code. So you first create the opt search options, which is just an empty struct, and then you use Gorilla schema decoder to just decode the query string into the struct, and all the fields are populated exactly how you would expect. And then in the other end, when you want to make an API request using parameters from some struct, then you use Go query string, which is by Will Norris from Google, and you just call query.values, and that'll take the struct and give you back a query string that is identical in meaning. So this has saved us a ton of code, and let us rely on the Go compiler to keep these things in check. We have a bunch of other tricks that we've done. I'm not going to go into these in depth, but maybe I will in another talk. We use something called appmon that we created, which wraps HTTP handlers and records timing information and errors in a Postgres database. That means for any front-end page that anybody sees on Sourcegraph, we can track all of the API calls that made up the data on that page and see which ones were slow. We also have a way of returning a typed error in our data store and having it be the same type even on the front end, which means that we can add additional logic to our errors. They're not just strings. And another nice thing is because we have a small number of really core interfaces, we made good test mocks of them, and we can use them throughout. We can use them when we're testing our front end, when we're testing our API client, API, and so on. All right, so that is the web app. And the second part of Sourcegraph is the standalone command line tool that you run to analyze the code in a project. So why code analysis? Why not just index the raw text of source files? Well, we think we can do better, and we think that to make a really good code search engine, just indexing the raw text of source files isn't enough. That's because we think that when you search for something, we should show you results that are the definitions you're looking for, the functions or the variables or the packages, not just files that contain the terms you typed in. We also think that search results should be ranked by the usage, by quality, by how recent they are, who else uses them, and so on, not just how many times the word you typed in appears. We think that once you go to a result, everything you're looking at should be fully linked, so you can click on any identifier in the code and you'll jump to its definition. And we think that when you're looking at a function, you should be able to see usage examples from everywhere else that function is called in the open source world, even in other packages. And let's be really clear about what code analysis is and what we mean by it. Sourcegraph has to understand code just like a compiler. That means every file it looks at, it has to know every definition in the file, every function, type, variable, parameter, and so on. And for each of those, it has to know its type, its package, its visibility, is it exported or not, and so on. And this varies depending on the language. Sourcegraph also has to know what every identifier in the source code refers to. And it also will look up some other information like dependencies. It will associate each definition with its authors based on VCS blame, and so on. So all this stuff is pretty complex, but we think it's worth it. And here's a really concrete example of what this looks like for a simple code file. In the top code snippet, we have a really simple code file. It has a function greet, and it makes a call to func.println in the standard library. So this is a call to something defined in another package entirely. And if we go to the directory where we've defined this code file and just run sourcegraph make, then we'll see what sourcegraph outputs for it. And there are two parts to its output here, the definitions and the references. The definitions includes the function greet, as we'd expect, and it includes information about its type and the fact that it's exported and so on. And it also says the character range where it was defined, from the 30th character to the 68th. And that helps us do code highlighting and jump to definition. Down below in the references, we see the print line reference. This is from character 49 to 56, and this reference info just says it refers to the standard library's func.println. And so on sourcegraph.com, that's how we would know that clicking on println should take you to the definition in the standard library. So this is a lot to pack in to a command line tool. It is essentially a compiler for many different languages and many different build tools. Thankfully, Go makes this super easy. It makes it easy to distribute, to compile, to compose, and to extend. And let's go into all of these. So the first thing is, this binary is super easy to distribute. It's 25 megabytes, totally static, no system or library dependencies, and it can be cross-compiled just by setting an environment variable. What this means is anyone can download it and run it immediately. So we save time, we have more happy users, and more people can analyze our code and become more productive with Sourcegraph. It's also easy to compile. In Go, for virtually every package or program, there's one command to compile it. And, this is something that doesn't get a lot of attention. People talk about how fast Go is to compile, but people don't talk enough about how simple it is to compile. In other languages, you have to deal with a whole host of build tools, setup.py, makefiles, pom.xml, and so on. But in Go, those files literally don't exist. It saves a ton of time. Now, if you have a really large program, you're probably going to have to add another tool to pin the package versions that you depend on. For this, we use Keith Rarick's GoDep, and it works great. It is not a major headache in our process. Another thing is that Go makes it really easy to compose the programs you make. Let's look at how this Sourcegraph make tool works, and then we'll dig in and see how it's easy to compose. When you run Sourcegraph make in a project directory, it goes and identifies every package in that directory recursively. So it will find Go packages, Python packages, Ruby gems, and so on. And based on all of that, it creates a plan for what it needs to do. And the format of this plan is just a standard make file. So this code snippet here is the output of running Sourcegraph make and telling it to just print the make file. You can see there are 3 make targets. One of them is to go and resolve the dependency of this Go package. One of them is to graph the Go package, which means produce the definitions and references. And another one, the third one, actually relies on the output of the second target and will determine for each definition who wrote it. We like to build complex things like this by composing simpler things. And so that's why we chose to use a standard make file. And that's also why we chose to not make this a monolithic process. Because you see, in each of the recipes in this make file, Sourcegraph just calls another subcommand of itself, another subcommand that does something very simple. So for example, Sourcegraph resolve deps will resolve the dependencies. Sourcegraph graph will just get the definitions and references. And all of these are, again, composed by Sourcegraph make, and that's using a standard format. So, this is really simple, and Go makes it really easy to build this program in this way, unlike other languages. And there's a few reasons for that. One is that Go executables start up really quickly compared to the JVM and interpreted languages. With the JVM, you often have at least a few seconds for it to start up, and with interpreters, it can depend on the system and how many libraries you're loading. And so it's much easier to think when you're working in those other languages to build a monolithic system that has one process that's long-lived, But in Go, you can adopt this really Unixy philosophy of composing your programs as Unix programs instead of as modules in the same memory space in some long-lived process. Another way that Go makes it easy to build composable programs like this is to re-invoke yourself or other Go programs. You don't need to worry about which include paths or class paths or dependencies or other things to pass as command line flags. You don't need to worry about which version of the JVM or interpreter you need to run. You just execute the Go program. And that's much simpler than in a lot of other languages. And so here the design choices that Go made early on in its design make it easier for you to build better programs. And that's a really important point. I think that a good language is one that leads you to do better things. And for us, Go definitely does that. So far, Sourcegraph make has detected packages in the repository and produced a makefile with the analysis commands that are necessary to actually perform the analysis. And the next step is for it to actually run these commands. And let's see what that looks like. So the main command that it'll run is this graph, which we also call analyze. And this will essentially look at a package and find all the definitions and references in it. When we designed Sourcegraph, we wanted our core code base to be language independent so that our code wouldn't be littered with if language equals Ruby or similar things. And so to implement a new language support in Sourcegraph, you implement a small number of interfaces. So analyzer, dependency lister, and a couple of others that I've left out. And these provide the key functionality to let Sourcegraph understand the structure of code in certain languages. So let's dig into this analyze, which again is what finds all definitions and references. And let's make a really simple analyzer. We have a sample JavaScript code file with some variables, some functions, open file, close file. And let's say that this is a real file and we want it to be on Sourcegraph. We want to be able to find how does everyone else use open file, what other projects call start file, and so on. So we want to implement JavaScript support for Sourcegraph. And the way to do this, again, is by implementing lang.analyzer and having it understand JavaScript. So here's a really simple implementation of lang.analyzer. You see we have the analyze method that takes in a file. And in this analyzer, we just run a regular expression at the top, var.jsdef, to find all vars and functions. Now, obviously, our real analyzers do a lot more advanced stuff like type checking and type inference. And our real analyzers are usually written in the language they analyze, not Go. But this should give you an idea of what it looks like. So once we've run this regular expression, then we just append to this defs list, which contains all the definitions. And the second code snippet is how we would run it. And this is pretty cool because we can take a JavaScript file and just get a list of all the functions and types and variables defined in it. So good. That is a really simple analyzer. But now what do we do? So we have this JavaScript analyzer, and let's say we have a bunch of other ones. And how does Sourcegraph know to call the JavaScript analyzer when it sees a .js file or a JavaScript package? There are a few ways we could do this, and the most common way will depend on which language you're using. So let's broaden our possibilities and consider what you do in general. So one possibility is we could pass a list of all the analyzers in our system as an argument to every function that would need that list. So we'd essentially be passing an argument around to a lot of functions. And this can be called a context object in Java. You see it a lot there. And this would require a lot of changes in our code, but it's a pretty simple to understand solution. Similarly, we could make every function that right now is a top-level function into a method on some type that has a list of these analyzers. Really simple, really similar to the first one too. And the third thing is we could have some global list of all of the analyzers in our system. So there'd be some global variable somewhere, and we would register the analyzers at static initialization time. So 3 options. And when we have a question about how best to design our Go program, we often consult the standard library in Go. Unlike in a lot of other libraries and languages, the Go standard library is a really high-quality source of design advice, and it's really readable. So we thought, where does the standard library do something similar to what we want to do? And one of the places is HTTP handle. Here they say we want to associate this path foo with some function to handle it. And what we want to do is essentially say associate.js paths with this JavaScript analyzer. So similar idea. And same with SQL.register to register a driver for a database. And there are a few other examples. And by the way, we have this motto that's don't ad lib, just crib for the standard lib. So you can use that in the future. We also looked in open source Go projects to see how they solve this same problem. Here's an example from Docker where again they use this handle or register type solution, which is the global variable. And there are a bunch of others. And so we decided to go with this approach. And here's what it looks like to get really concrete. There's a var analyzers, which is a global variable, and then there's a register function that just takes the language.js and an analyzer and it just adds it to the map. And then the way that we register the JavaScript analyzer or other analyzers is in the package that defines them at static init time, we just call lang.register and hook it up. And then when we want to build the final program that contains all these various analyzers, we just import them for side effects with import underscore. And so this is a super simple solution. It's maybe 10 lines of code. But remember, the solution that we chose used a global variable. For some of you, that might be ringing the alarm bells right now. Because in a lot of languages, this simple solution using a global variable would be frowned upon. And actually rightly so. Why is that? Well, two things. So one, it uses static initializers. In a lot of other languages, such as Java and Python, the static initialization order is not well defined. You don't even know that all the static initializers will be finished when your program begins, when the main function runs. You don't know if a static initialized variable that depends on some other value, you don't know that that value will be ready in time. And so you can't make these assumptions that it will just work in the same way you can in Go. And another thing is our solution, again, uses global variables, which can make code harder to reuse and refactor and test. And in other languages, if you have global variables, in Python, for example, it makes it harder to refactor because you don't have a type system to let you know what is everywhere that points to that global variable. In Java, for example, it can make it harder to test because if you have a lot of tests that all touch that global variable, and for each of those tests you want to change it, then you don't have any way of isolating one test's view of that variable from the rest. So, this solution is not necessarily a good solution, except in Go. And that's the point of this exercise. Go's design makes this really simple solution okay. It actually makes it a really good solution. Why is that? It's a bunch of reasons, and they're all because of very deliberate decisions that the Go team made, I think. So one, there are first-class global variables in Go. You don't have to have some singleton class in Java or some other kind of language construct that's much more complex. In Go, it's one line, var, whatever, and it's in the package level. Another thing is in Go, static initialization is really well thought out. It occurs serially, so you can't have multiple initializers running at once. It occurs in the sensible order, so the things that any static initialized value needs will be ready by the time it runs. And all your initializers will complete before main runs. Those guarantees are really important. Another thing is for testing, in Go, each package's tests are run in a separate process, so they can safely modify global variables and not have to worry about other packages using those variables or even modifying them themselves. And then the fourth point is really important. It's a cultural point, and it's that the standard library and a lot of big open source projects using Go, and the whole Go team uses this solution and actually embraces this kind of really simple solution. Other communities are going to shun you for this solution, and in other communities, people might build their programs so that they would break if you used static initializers and global variables in this way. But in Go, people expect this, and it's acceptable. All right, so that's it. So we have seen the large web app, which takes the data in the database, and we've just seen how we produce the data from just any code directory. And that JSON we saw out of the analyzer will go straight into our Postgres, and that is what you see on Sourcegraph.com. So that's it. Thanks for watching. You can try out Sourcegraph now at Sourcegraph.com. We'd love to hear your feedback, and contact me if you have any questions. I'm at SQS on Twitter or SQS at Sourcegraph. Thanks.